Hello, hello. So I will wait for so I will wait for 2 minutes, then I will start. Okay. So good afternoon, everyone. I am Keshav. This is online problem solving session of week 4 applied numerical method course ME 111. Okay. So this is what this is online problem session. session, week 4 of NPTEL course NME111, okay, which is applied numerical methods. Should I start now? Please respond in the chat box. If I am okay, so we will start. We'll start now. So I hope you have gone through the lectures that has been provided by the instructor for week 4. The first topic that he discussed is LU decomposition method. Okay, this LU decomposition method, this can be used to solve system of linear equations. Okay, system of linear equations. So as earlier, first we will try to discuss or brush up or revise the things that has been covered by the instructor in week 4. Then we will try to solve some sample problems that will be similar to the problem that has been given to you in the assignment of week 4. Then we will try to write a computer program that will help you to write programs related to week 4's topics. Okay, so you have heard about in week 3 the instructor had discussed about Gauss Gauss elimination. So what is the problem with Gauss elimination? Suppose I want to solve AX equal to B type of problem. Okay, this is what this is a system of linear equation in matrix notation. Okay, so I do not want to solve this equation. I want to solve some set of system of linear equations. Suppose AX equal to B1, AX equal to B2, AX equal to B3. Okay, so by using the Gauss elimination method, we can solve this equation, we can solve this equation, we can solve this equation. But this equation will involve a set of calculations. Okay, similarly, this equation will also involve the same set of calculations. This equation will also involve the same kind of calculations. But since A is same in all three equations, so if we can do something with this AX term, then use this B1, B2, B3 and try to save the calculation that is involved. So that we can do by using LU decomposition method. So this LU decomposition method is very beneficial when we try to solve a set of system of linear equations such that for a particular type of A, there are many B's. Okay, means AX is equal to B1. Similarly, a different set of system of linear equation, we have AX equal to B2, Suppose we want to solve both the equations, both the set of system of linear equations. Then in that case, using LU decomposition will be very beneficial for us. What we do in LU decomposition, if I summarize, simply suppose we have an equation. Okay, so suppose we have a Ax equal to B type of system of linear equation. Okay, this we have. So what we will try to do, we will first try to we will first try to we will first try to decompose A into U and L. U is what? U is a upper triangular matrix and L is a lower triangular matrix. So what we will try to do, we will simply decompose the coefficient matrix into two matrices, L and U, where L is a lower triangular matrix and U is a upper triangular matrix. Then what we will do? Then we will try to solve L D equal to B type of problem. L D equal to B type of problem. So what is this D we are trying to find? Since L is a lower triangular matrix, to solving this equation, L D equal to B will not require any elimination process. Suppose we have some equation like that. 1, 2, suppose lower triangular matrix. No? So I need to make a lower triangular matrix. Suppose 1, 2, 0, 3. Okay. This is a lower triangular matrix. Suppose some D1 I have, some D2 I have. Okay. This is equal to some B1, some B2. Okay. So from here, directly I can find D1 equal to, if I see this set of equation, this will be multiplied by this, and 0 will be multiplied by D2. That will lead to the D1. D1 will cut through B1 without any elimination. We got the value of D1. Now in the second equation, what we will get? 2 D1 plus 3 D2 will be equal to D2. So D1 already known, D1 known, to D2 is only unknown. So this we can solve directly without any elimination process. Okay. So only by substituting the value, we can get the value of D1. So since we solve this LD equal to B in forward fashion, first line has been, first row has been solved, then second row, then third row. So this is called forward substitution. Then once we got LD equal to B, simply now we will solve we will solve ux equal to d. Okay, ux equal to d. See, u is a what? Upper triangular matrix. So by using the backward substitution method, like we did in Gauss elimination, by using this backward substitution method, we can find the value of x without using any elimination. Okay. Now suppose our B is changing. Okay. So once we have decompose A into L and U form, for any value of B, we can put the B here directly, and without using any elimination, by doing the forward substitution and backward substitution, we will be able to find value of X. Okay, fine. Please respond. Hello. Hello. Am I audible? Please respond. Okay. Okay. So here is the theory. LU decomposition. If A is an invertible matrix, then A can be decomposed in L and U form. Then AX equal to B can be written as LUX equal to B. And simply if I multiply, if I multiplied some Y in this equation, so what I will get? LUX Y equal to BY. This I can write as LY UX equal to B. y. So I can assume that these two are equal, and I can assume these two are equal. By assuming this, we can solve this problem like that. L equal to Ly equal to b, then ux equal to y. How we can find the value of y? By using the forward substitution without any elimination process. Okay. Similarly, I can solve this ux equal to y problem and find the value of x using backward substitution method. Okay, without any elimination. So let us revise what we have did. What we have did in Gauss elimination. Suppose we have a problem 3245 x equal to 59. Okay, this is my a, this is my x, this is my a, this is my x, and this is my b. Okay, now if I want to solve this equation, this system of linear equation by using Gauss elimination method, what I can do, I will simply try to make this term as 0. I want to make this term as 0. So what I will do, this is my pivot point. So simply what I will do now I will do, I will multiply, I will multiply, I will replace the equation 2 with equation 1, sorry, equation 2 minus the term whichever here divided by pivot point multiplied by equation 1. Okay, once I will do this, I will get this values of a. Okay, 3 2, this will remain same, and the row 2 will change. The values that are below pivot will become 0, and other value will come something. So then this is converted into a upper triangular matrix. Now by using the backward substitution method, we can find the value of x and y. Okay, so what we have did here, we simply multiplied with an elementary matrix in our matrix A. Okay, so this is my elementary matrix 1 0, and in row 2 what I have did, for equation 1 means for row 1 I have multiplied with -4 by 3, and row 2 as it is. Okay, then I have summed it. So simply by doing the elementary operation, I have converted it into a upper triangular matrix. So this E, by seeing this, we can see that this E is an what? This E is a lower triangular matrix. And this will come always a lower triangular matrix. You can do for other cases also. You will get. So simply, what is our U here? U is E inverse A. So this E inverse will also be a lower triangular matrix. So this is a corollary that a inverse of a lower triangular matrix will be always a lower triangular matrix. The instructor has proved in the lectures also. You can go and see that a inverse of a lower triangular matrix will be a lower triangular matrix. Similarly, if I write it in a generalized sense, so this elimination I do by multiplying many elementary matrices. Suppose first I take first row, first element as a pivot, then second row, second element is a pivot, third row, third element. Then for every pivot, I will get a elementary matrix. Okay. Then by multiplying this elementary matrix, I will get these all are lower triangular matrix. This is also a lower triangular matrix. This is also a lower triangular matrix. This is also a lower triangular matrix. So overall, the product will also be a lower triangular matrix, since the product of a lower triangular matrix will be always a lower triangular matrix. So in generalized sense, we can say that EA equal to U. So E is what? E is my lower triangular matrix. This is my upper triangular matrix. A is my coefficient matrix. So if I move E to the right hand side or multiply the equation both sides with E inverse, I will get A equal to E inverse U. This E inverse is a lower triangular matrix. So this I can write as A equal to LU. Okay. So from here it is came. Okay. So if I have AX equal to B type of problem, so I want to solve this using LU decomposition method as a version of Gauss elimination. So what will be my L? My L will be 1 1 1 on the diagonals, and these are the factors that we'll use to multiply. Okay, F21. So F21 will be what? F21 will be the factor that I will use to multiply in equation 1, then subtract in equation 2. Okay, so this is my F21. Similarly, this is my F31. Similarly, F32. Okay, and what will be my U? My U will be a, this will be the same, and this will be the replaced value. If you use this L and this U, if you multiply that, then you will get the same matrix. You can show by simply multiplying L and U, then whatever element you are getting, you just replace F21 with these formulas, F21, F31, and F32. Then you will get the same value A. This same A you will get if you multiply L and U, this and the formula. Okay. So once L and U are known, you know the procedure how to solve it. Simply take L, take some arbitrary D, then find the L multiplied by D equal to B and solve this for D. Okay. Once you will get the value of D by simply doing the forward substitution method, then you can solve Ux equal to D problem you very easily by using backward or back substitution. Backward. Okay. So now if you see here, suppose I am assuming in general some L is what? Some L is a lower triangular matrix, so upper part will be 0. Suppose 3 cross 3 I am taking. So L11, 0, 0, L21, L22, 0, L33, 1, L32, L33. Okay. Similarly, my U is a what? Upper triangular matrix. So U11, U12, U13, 0, U22, U23, 0, 0, U33. So if you multiply this, then it will be what? A will be equal to L multiplied by U. This will be my what? A. So here, what are the unknowns? This is my one unknown. This is unknown. This is unknown. So 6 unknown from L, 6 unknown from U. And how many elements we have in A? 9 elements. So how many equations we have? We have 9 equations. But how many unknowns? Unknowns we have 12. Okay. So this cannot be solved. That's why what we do, we simply assume the diagonal value of either L or U matrix as 1. Okay. So if I assume the diagonal elements of U matrix as 1, then it is called as Kraut method. Okay. Kraut method of LU decomposition. Okay. LU decomposition. If I assume the diagonal element of U matrix as 1, then it is known as Kraut method. If I assume the lower matrix diagonal element as 1, then it will be called as Doolittle method. Okay. Doolittle method of LU decomposition. Now what we have? Now we have 9 equations, 9 unknown. This can be very easily solved without any elimination. If we do in right order means what? Either we go move row wise or we move column wise. Means what? Either we move like that. Suppose first I solve the for this element, I equate for this element, then this element means I go like that, then I go like that, then I go like that, then I will able to find the values. Or I can start from here, I go downward first, then in the second column, in the third column. If I move in the right order, I will able to solve this problem without any elimination process. Okay. Okay, so we'll maybe move forward now. So basically what we have seen, to solve for solving the system of linear equation, we can solve either using the Gauss elimination process, or we can solve by using this LU decomposition method. Okay. Now, if we want to solve a system of non-linear equation, okay, system of non-linear equation. In the first week, we have seen that if we have one equation, one non-linear equation, that we can solve, that we have seen that we can solve using either bisection method, or what was the second method? Newton-Raphson method. Okay, second method was Newton-Raphson method. So what we have did in the Newton-Raphson method, whatever the function we have made some initial guess. Then we have assumed at the initial gates my function is what? Linear. So my function is what? Linear. So what, wherever it has cut the x-axis, that was my root. Okay, that was my root. Now, taking this as the initial guess, we draw a tangent from here. Wherever it cuts, this will be my second root. This, like that, we move, and we found the root of a equation. Okay. So if we have rather than one equation, we have n number of equations. Okay, so we have some function f in an arbitrary n variable x1 x2 dot 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 xn. Here this I is from 1 2 3 to n. So this means what? We have some first non-linear equation as f1 operated on this n dimensional space, then this f2 x1 x2 dot dot equal to 0. Similarly fn x1 x2 x3 dot dot xn. Okay, so this is n non-linear equations that we have. Okay, so if you remember, we have seen, this is the that I have discussed, that is a what? Geometric interpretation of Newton-Raphson method. Whatever we have drawn this function, we draw some tangent wherever it cuts. This is my guess again, I draw tangent. So this is what geometric interpretation of Newton-Raphson method. Similarly, we have seen the Taylor series representation of Newton-Raphson method, where what we have done in Taylor series representation, we have linearized the Taylor series to get the Newton-Raphson formula. Okay, so similarly, we will use here also the Newton-Raphson, this Taylor series expansion, to express the system of linear equation, and we will solve using Newton-Raphson method. Okay, so if I expand, so what I assume that my last last iteration, means at the kth iteration, I have found some values of, or the root of the system of linear equation, means of x1 kth iteration, x2 kth iteration, x3 kth iteration, dot 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 xn at the kth iteration. This I have found in the kth iteration. What I assume now, that when I move from kth to k plus 1th iteration, I will find the actual root. Means what? This will be equal to, my functions will go to 0. Okay, in the k plus 1th iteration. This is my assumption. Now what I will do, I will simply express x k plus 1th iteration function at x plus kth 1th iteration as a Taylor series expansion. Means fx plus summation of j equal to 1 to n delta xj. I assume xk, sorry, xk plus 1th iteration is equal to sum xk plus delta x, sorry, delta. Okay. Now for any j, I can write as xj plus j. Okay. This is, then I have simply expressed in a Taylor series expansion, and I will do, I will linearize the equation. Means what? I will neglect the second order, third order, and other higher order terms. Okay. And I am assuming that at k plus 1th iteration, my function will go to 0. Means I will get the actual value. That's why I have put this at 0. Now what I will get? We will get this equal to this. Okay. So what if we express this for, if I put simply I values, so I will get n equations. Na? So xj del f1 del xj at kth iteration will be equal to minus f of 1 at the kth iteration. Similarly, for 2 I will write, for 3 I will write, then dot 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 for nth equation I will write. So this is what, this is my known value. Okay, this is what, this is also my known value. So only delta x j is unknown. Okay, so I simply, what I have got, I have found, I have found system of linear equation in delta x j. Okay, so if I solve this system of linear equations, how I can solve the system of linear equation? I can solve either using the bisection method, or sorry, either using the Gauss elimination method or LU decomposition method. Okay, once I will solve this, I will get the xj's values. Okay, then simply I will add this xj value in x kth iteration plus delta of xj value, that will give me xj at k plus 1th iteration. Okay, once I will found this value, then I will move for other iteration, next iteration. Okay, so this whatever the differentiation form I have found, or the coefficient matrix that we have found, this I can express in term of a matrix. This is known as a Jacobian matrix. Okay, Jacobian matrix is what? The Jacobian matrix is matrix that is formed by the differentiation of the function. So any element in J I can represent as Jij will be equal to what? Jij will be equal to del of f of I divided by del xj. Okay. So system of non-linear equations can be solved by using the Newton-Raphson method, that will convert the system of non-linear equation into a system of linear equation that can be solved using Gauss elimination or LU decomposition method. Okay. So till now, whatever we now will again move back to system of linear equations. Okay. We will now move back to system of linear equation. Okay. So till now, whatever we have discussed, that is known as a direct method to solve a linear equation. Okay, system of linear equation. There we have discussed Gauss elimination method, then LU decomposition. Similarly, there are iterative methods to solve the system of linear equations. Here what we will discuss, we will discuss Jacobi iteration and Gauss Seidel iteration to solve the system of linear equation in the iterative fashion. Okay, so what is linear equation? Suppose we have a linear equation AU equal to B. AU matlab simply x is replaced by u here. So u is the variable that we want to find. Okay, so AU equal to B. So in this system of linear equation,
we will make some initial guess u at 0th iteration. Then we will create a sequence u1, u2, u3, ukth iteration, and we will put some stopping criteria that u a multiplied by u at kth iteration minus b. If it is smaller than some user defined epsilon, then we will stop. Okay. So first we'll see what is the Jacobi iteration. Now we'll see the Jacobi iteration. So simply we have taken here two linear equation, 10 u1 plus u2 equal to 11, u1 plus 10 u2 equal to 11. By seeing this, you can say that this is the solution u1 equal to u2 equal to 1. Okay. So what we will do in Jacobi iteration, suppose we have assumed first equation for u1 and second equation is for u2. So from first equation, we will find the value of u1. So this u1 can be expressed as this. Similarly, u2 can be expressed as 11 minus u1 divided by 10. Okay. Then we make some initial guess u1 equal to u2 and any initial guess. u1 equal to, suppose u1 at 0 to station I have assumed 1, u2 at 0 to station I have assumed 2. So 1, 2, like that. You can assume any initial guess. Then what we'll do, we will put these and these values in the equation. Okay. u1, u2 I will put here. Similarly, this u1 I will put here. Then find the value of u1 and u2 at the first equation. Okay. Then I will use these values and put in these equations again, this equation and this equation. Then get u1 and u2 at second iteration. And I will move like that. Then suppose my stopping criteria was epsilon was some 0.00001. So once my u1 at the k plus 1th iteration minus u1 at the kth iteration, their absolute value will be less than this, then I will stop. Okay. Now same thing I can represent. Now earlier I have expressed as some example. Now I will try to explain in a generalized fashion. In generalized fashion, I can say that some equation I have a u equal to b. This can be represented as j equal to 1 to n aij uj equal to bi. So this I is what? My number of equations. This j is representing the number of variables. Okay. So to solve the equation, this will be equal, na? I will be equal to j. Okay. Now what I have done here, simply suppose first equation is my u1 equation. Na? So I will keep u1 in the left hand side and put all other terms in the right hand side. So my u1 will be equal to b1 minus summation of j will now go from 2 to n. A I will be replaced from what? I will be 1 I a 1 j uj at u k minus 1th iteration. Okay. Similarly, u2 will be what? u2 will be b2 minus this first term will come a21 u1 k minus 1th iteration minus j now will go from 3 to n. This whole will be divided by a to 2. Okay. Similarly, in general fashion, I can write uij at the kth iteration will equal to bi minus u1. J will go from 1 to n, but j will not equal to I. aij uj at k minus 1th iteration divided by aii. Okay. Now in this equation, what I can do? I can simply add aii ui at the k minus 1th iteration. I can add and subtract. Then I can represent this as bi minus summation of aij uj at k minus 1th iteration. J will go from 1 to n. Okay. So this is my kind of left hand side of the equation. This is my left hand side of the equation, and this is my bi. So if I subtract right hand and left hand, this will give kind of residue. This will give some residue to me. Okay. So this same I can write as ui at the kth iteration
that will be equal to ui at the k minus 1th iteration plus ri is what? Residue at kth iteration divided by aii. So this whole term I called as correction. Okay, so ui is what? So ui at the kth iteration will be equal to ui minus ui at the k minus 1th iteration plus correction. Okay, this is my formula for Jacobi iteration. Okay, now we'll see the Gauss-Seidel method. Okay? Gauss-Seidel method is also similar to the Jacobi method. Only one thing is different. The difference is, earlier suppose I have assumed guess I have made the guess u1 at the 0th iteration, u2 at the 0th iteration. So this is my 0th iteration value. So in the first iteration, I will use these values to find the new values in the first iteration. But in the Gauss-Seidel, we will use the latest value of u in RHS to find ui. Okay, what do you mean by that? Suppose let's take an example here. 10 u1 plus 20 u2 plus u3 equal to 31. 20 u1 plus 10 u2 plus u3 equal to 31, and third equation is u1 plus 10 u2 plus 20 u3 equal to 31. Okay, these three equations we have, and I wish to solve this equation using Gauss-Seidel method. Okay, so if I write this is, I assume first equation is for my u1 variable, second equation is for u2 variable, third equation is for u3 variable, like that. So I write u1 will be equal to what? 31 minus 20 u2 minus u3 divided by 10. Okay, similarly u2 will be equal to 31 minus 20 u1 minus u3 divided by 10. u3 will be equal to what? u3 will be equal to what? u3 will be equal to 31 minus u1 minus 10 u2 divided by 20. Okay, if it was a Jacobi iteration, what I would have done, the kth value will be equal to k minus 1th iteration values in the right hand side. Okay, this is will be the same as the Jacobi iteration. But while solving the second equation, means finding the value of u2, what I will do, I will replace u1, I will put the u1 value of kth iteration, not k minus 1th iteration, means the latest value. Since just above I already have found u at the kth iteration, I have found the value, so now I will use the latest value here. Okay, similarly here, if I want to find u3 at kth iteration, so rather than k minus 1th, kth iteration value will be used to solve the equation. Okay, so this is the small difference in Gauss-Seidel and Jacobi iteration. This is a small difference, but it will improve our solution very much. The solution will converge very rapidly. Okay, compared to the Jacobi iteration. Fine. Means what? Suppose I have a u, this can be represented as like that. We have already represented it. So residue what? Same residue as earlier. Okay, no, residue is different now here. So now what will be the my residue here? Ri will be equal to, suppose ith equation I want to write the residue value. So Ri will be equal to Bi minus j will go from 1 to I minus 1. There I will use u at kth iteration value only, and for I to n I will use u k minus 1th iteration value. Okay, this will be my residue. Other thing will be same as the Jacobi iteration. Okay, and equation will be same as uk, u at the kth iteration will be equal to u at k minus 1th iteration plus correction will be ri divided by aii, but this ri is different from Jacobi iteration. Okay, what will be the stopping criteria? Some stopping criteria will make this uk at the kth iteration minus uk at k minus 1th iteration, if it is smaller than some epsilon, then I will stop. Okay, fine. Okay, so we'll move further. So in Gauss-Seidel method, if you see, now you see Gauss-Seidel method with successive over relaxation. So here what we are trying to do, we are finding the value at kth iteration, 2k minus 1th iteration plus some correction. Okay. So if this correction is very small, okay, if this correction is small, what it will do? Our equation will converge very slowly. Okay, this equation will converge slowly, which means what? I will need large number of iterations to solve the problem. Similarly, if this correction is very high or very large correction, then what? Then what? It may happen that my equation may not converge. Okay, so these two problems may arise. Suppose I have corrections. I have some u1 equal to 1, u2 equal to 2. Okay, my actual solution is 1.5 and u2 is 2.5. But I got the correction value as 2 for u1, and for u2 I got 3 value. Okay, so I will go much farther to my actual solution. In that case, my solution may not converge. Okay, so what we'll do to avoid these two issues, we'll use successive over relaxation method. What we will do in successive over relaxation method, we find simply we multiply some w with the correction. This w is known as a relaxation factor. If this w is equal to 1, this will be what? Classical Gauss-Seidel method. But if this w is greater than 1, then this is known as over relaxation. Okay, this over relaxation will lead to fast convergence. Okay, but as we say that if this correction is very high, the solution may not converge. So generally w should not be taken greater than 1. So w usually is less than 2. Okay, and if my w is between 0 to 1, then this process is known as under relaxation. Okay, successive under relaxation. This will lead to slow convergence, but this is the method that usually used in the commercial softwares. Okay, what it do? It try to stabilize the solver. Okay, so suppose you are doing solving some CFD problem in ANSYS. So what if you use some TDMA method, the Thomas algorithm to solve the linear equation or some method? There, if you are using Gauss-Seidel method, that will be inherently using the under relaxation method. Okay, fine. Should we move ahead? Now, then after that, whatever we have discussed, its theory was also discussed by the instructor. There, what means what? This coefficient matrix A is decomposed into E and F, such that the taking of inverse of E is very easily. This inverse of E we can take very easily. Okay, so we wish to convert A U equal to B type of problem, A equal to B type of problem into U equal to MU plus C type of problem, where M is equal to minus E inverse F and C equal to E inverse B. And since E is easily invertible matrix, so this we can solve very easily. Okay, invertible means not that we will invert it. Invertible means we will solve by some linear solvers. So what we try to do in Jacobi iteration, we try to make E as a diagonal matrix and F as zeros at the diagonal. Okay, then simply D inverse will be equal to the diagonal matrix, where element will be equal to, rather than AII, it will be equal to 1 upon AII. Okay, and once we have found the D, then we can easily find this M matrix that will lead to I minus D inverse A, and this C matrix D inverse multiplied by B. In Gauss-Seidel, what we try to do? we try to make E as a lower triangular matrix and F as a strictly upper triangular matrix. Strictly upper triangular matrix means it will be upper triangular matrix, but it will have zeros at the diagonal. Okay, that will lead to M equal to I minus L inverse A, as C will be L inverse B. Okay, then convergence criteria for the iterative solvers. Okay, so there is a criteria known as the Scarbo criteria. This Scarbo criteria is proposed for a Jacobi tracer, but it can be applied to Gauss Seidel also. What it is a sufficient condition. Means what? Sufficient condition, it is not a necessary condition. Means what? Maybe our equation do not such our system of equation may not satisfy the Scarbo criteria, but still it converges. Okay, so suppose I have A equal to A11, A12 dot dot A1n. This is my coefficient matrix. So this matrix should be diagonally dominance. Diagonally dominance means we have what? For all rows AII, this absolute value should be greater than or equal to summation of other elements in the row. Okay, greater than or equal to, and for at least one row, it should be greater than. If this two condition is satisfied, this is known as diagonally dominance condition. Okay, if this is satisfied means what? My equation will converge always. Okay, then solution may converge with or without Scarbo criteria. Okay, with or without Scarbo criteria. This is developed for Jacobi tracer, but it may be successfully applied to Gauss Seidel. Okay, then till now what we have discussed in linear algebra problem, solving system of linear equation Ax equal to B type of problem. This is what? System of linear equation. System of linear equation. Okay, and we have also seen system of non-linear equation. Non-linear equation. There also we have converted it to a system of linear equation only. J delta x equal to B type of problem. Now we have converted it to J. J was what? Jacobian matrix, and delta was my variable, and B was my right hand side. So system of non-linear equation also we have converted to a system of linear equation. So till now we have seen how to solve a system of linear equation. Means what? Ax equal to B type of problem in linear algebra. Okay. Now we will see second type of problem, which is known as eigenvalue and eigenvector type problem. Means what? Now we'll see A V equal to lambda V type of problem, where A is what? A is a square matrix, V is the eigenvector of the matrix, and lambda is eigenvalues of a matrix. Okay. Now, if you do not able to record what is eigenvalues of a matrix, eigenvectors of a matrix, you can refer to a textbook. Okay, any linear algebra textbook. Advanced Engineering Mathematics by Physics, you can go and read if you want. So here we will see numerical method to find the eigenvalues and eigenvectors of a square matrix. Okay, so how we, in analytical sense, how we can find the eigenvalue? We can first find the characteristics polynomial. The characteristics polynomial is what? Suppose A is my matrix, then determinant of A minus lambda I will be my characteristics polynomial. Okay, then this determinant of A minus lambda equal to 0 will lead to eigenvalues. The root of this characteristic equation will give me the eigenvalues. Okay, then we'll find the eigenvectors. Okay, suppose if we want to solve this A equal to 7 3 6 4, I want to find the eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors of this matrix. So what we'll do, first I will write determinant of A minus lambda I. So A minus lambda is, if I write, to simply 7 minus lambda or minus lambda. If I want to find this determinant, this will be multiplied by this minus this will be multiplied by this. This will lead to lambda 1 equal to 10, lambda 2 equal to 1. Okay. So these are my eigenvalues. This is my higher value. So this is my dominant eigenvalue. This is my other eigenvalue. Now how I can find the eigenvector? I can write for any eigenvalue. I can find the eigenvector by a v1 will be equal to lambda 1 v1. Okay. Or simply a minus lambda I v will be equal to 0. So simply put the a and lambda values, lambda 1 here. If I put, I will get this equation minus 3 3 6 minus 6 v1 will be equal to v2. If you see and solve this equation, you will get v1 will be equal to 1 and 1. Okay. Since if we have found a v means an eigenvector, then its linear combination or linear combination will lead to, then its linear combination will lead to the eigenvector of the same corresponding eigenvalue. Okay. Means that if I found the eigenvector, then its linear combination will also be eigenvector. Okay. So if I found for corresponding to lambda 1, if I have found corresponding to lambda 1 some eigenvector v1, then its linear combination means what? Some a multiplied by v1 or some a multiplied by v1, that will be also eigenvector corresponding to lambda 1. So generally what we do, we try to normalize. So it is a usual practice to simply normalize it. Okay. So suppose 1 1 was my eigenvector, so I divide with the norm of the eigenvector, then I will get the normalized eigenvector. Okay. This, I think you already know this procedure to find eigenvectors and eigenvalues. Okay. So here we will see methods or numerical methods to find eigenvalues and eigenvectors of a square matrix. Okay. So first method is power method or power iteration method. Okay. What we do in power method, suppose we have any n cross n diagonalizable matrix, means what? If its rows, its eigenvector are linearly independent. Okay. This matrix we have, then I can compute lambda 1 and v1. Where is lambda 1 is what? Dominant eigenvalue. Okay. Dominant eigenvalue means its absolute value will be greater than other absolute values of eigenvalues. Okay. It will be the maximum value. It will have the maximum in absolute sense. Okay. So how this algorithm will start? I will assume some eigenvector. Okay. Then what I will try to do? I will try to solve vk plus 1th iteration, means eigenvector at k plus 1th iteration, that will be equal to a multiplied by v at the kth iteration till convergence. Okay. And if I simply normalize it, then what I will get? I will get v hat at k plus 1th iteration, that will be equal to a v hat at the kth iteration divided by norm of a multiplied by v hat. Okay. And this will lead to my eigenvalue at the k plus 1th iteration, that will be equal to a multiplied by v hat inner product, means the dot product of v hat at the kth iteration. Okay. So these two equations are my important equation for power iteration. What power iteration will give? Power iteration will lead to a dominant eigenvalue and corresponding eigenvector. Okay. Okay. Then I will put some stopping criteria, that my lambda at some k plus 1th iteration minus lambda at some kth iteration, if this is less than some user defined value, small value, then it will give me what? It will be my stopping criteria and my program will stop there. Okay. So by using the power iteration, I can find what? I can find the dominant eigenvalue. But what about the other eigenvalues? So suppose if I want to find the other eigenvalues, that I can find by using the inverse power method. Okay, inverse power method. How we can find using inverse power method? Suppose we have some A square matrix. So it's if its eigenvector is V and eigenvalue is lambda, then I can write A V equal to lambda V. Okay. Now what I will do, I will add Q sum scalar multiplied by identity matrix multiplied by V. Okay. I will subtract this QIV in both sides. Okay. So this will lead to what? A minus QI V will be equal to lambda minus Q V. Means what? Now this is my square matrix and this is its corresponding what? This is its corresponding eigenvalue and V the same eigenvector. Okay. Okay. If I take the inverse, so this will lead to this equation. Now, if you can see this can be deduced from the linear algebra theory that the if A eigenvalues of A is eigenvectors of A is V and eigenvalue is lambda, then what will be the A inverse eigenvector will be same V, but this eigenvalues for A inverse will be 1 upon lambda. From there also you can deduce this equation. Okay, this equation. Okay, so if I write lambda minus mu lambda minus q equal to mu, this whole term as mu, so this will be give me A minus q I inverse will be equal to mu V. Okay, so if A is my A is my matrix, then its eigenvalue will be lambda and V. If this is my square matrix, then lambda minus mu whole reciprocal will be my eigenvalue and V will be my eigenvector. And if I put q simply q as 0, then mu will be what? Mu will be my eigenvalue and V will my eigenvector. Okay. If I simply put q equal to 0, that will lead to, and I solve using power method, then that will lead to mu max. Okay. So from there I will find mu max, and this mu max, if I take reciprocal, I will find the lambda minimum of A matrix. So by using this method, I can easily solve for smallest eigenvalue of the matrix. Okay. And for other values, how I can go? I can choose any q such that any q, this is called as shifting parameter. Any q I can choose such that lambda j minus q, if I take magnitude, lambda j minus q, if I take its magnitude, if this is very close to lambda j, if I q says such that if this condition, this inequality satisfied, then I can find other eigen values. Okay. By using this formula, I can find other eigenvalues. Okay. So as we know finding inverse is not easy. What we'll do, rather than solving this equation, we will solve this equation. This is what A V at k plus 1th iteration will be equal to A V at the kth iteration. This we already know. This A we know. This we want to find. So this is what? This is a system of linear equation. System of linear equation. This can be solved by Gaussian elimination or other techniques, other linear solvers. Okay. Fine. So this is what has been discussed by the instructor in this week, this week 4. Okay. Okay, fine. Now we will solve some problems. Okay. Some sample problems that will be similar to the assignment problem of week 4. So now I will show the problem and now you try to answer in the chat box. Okay. Then I will also solve the problem. Okay, so we'll solve the first problem. So this, let me add one page. Okay, so this is my first problem. Please solve this problem. Problem is what? 2x plus y equal to 3 and 3x plus 2y equal to 3. Initial guess is my x equal to y equal to 0. Then we need to find x and y after first iteration. Okay, this we want to solve using Jacobi iteration. Okay, please pause the answer while solving this equation using Jacobi iteration. Initial guess is what? X equal to y equal to 0, and we want to find x and y value after first iteration. Okay, so what is my equation? 2x plus y equal to 3 and x plus 2y equal to 3. Okay, please try to solve and post the answer. Meanwhile, I will also solve here. Okay, so this is my equation for x. So x will be equal to, from here, what? 3 minus y divided by 2. From here I will get y equal to what? 3 minus x divided by 2. Okay, so from here x at the first iteration, that will be equal to 3 minus y at the 0th iteration divided by 2. Similarly, y at the first iteration will be equal to 3 minus x at the first 0th iteration divided by 2. Okay, if I simply put the value 3 minus 0 divided by 2, that will lead to 1.5. Okay, similarly here 3 minus 0 by 2, that will lead to 1.5. Okay, fine. Now I hope you also got the same answer. Now the same equation we want to solve using Gauss-Seidel iteration. Okay, the initial guess is same, x equal to y equal to 0. We want to find x, y after first iteration, but this time we want to solve this problem using Gauss-Seidel method. Okay, so in Gauss-Seidel method, what? The latest value will be used for equation 1. X at the first iteration will be equal to 3 minus y at the 0th iteration divided by 2. Y at the first iteration, that will be equal to 3 minus x at the 0th iteration. Rather than using the 0th iteration value, we'll use the latest value. Since we have already found the x at the first iteration, we'll use the latest value. Okay, so this will lead to same 1.5, but here 3 minus, rather than 0th iteration value, we will use the first iteration value, 1.5 divided by 2. So that will lead to y will be equal to 0.75 at the first iteration. Okay, x will be same. Fine. Okay, these two are very easy problems. Now third problem: if eigenvalues of a matrix 3, 4, 0, 2 are lambda 1 and lambda 2, then we wish to find the value of this lambda 1 multiplied by lambda 2 minus lambda 1 minus lambda 2. So we want to find the value of this expression. Okay, okay, so now please solve this third problem. If eigenvalues of 3, 4, 0, 2 matrix is lambda 1 and lambda 2, we want to find lambda 1 multiplied by lambda 2 minus lambda 1 minus lambda 2. So simply you need to find first the eigenvalues of this equation. Once you find, you can put here in this expression and find the value of this expression. Okay, so what I want to do, what is my equation A? Sorry, the matrix is square matrix A, 3, 4, 0, 2. So my matrix is 3, 4, 0, 2. So what will be my characteristic equation? determinant of det of a minus lambda I will be equal to 0. Okay, so if I write here 3 minus lambda 4 0 2 minus lambda, okay, equal to 0. From here it will lead 3 minus lambda 2 minus lambda minus 0 equal to 0. This 0 I simply remove. So this will lead to what? This will lead to lambda equal to 3 comma 2. Okay, so this is my value of lambda. Na? This is my eigenvalues. Now any expression I can find here, I need to find lambda 1 multiplied lambda 2 minus lambda 1 minus lambda 2. This will be equal to what? 3 multiplied to 6 minus 3 minus 2. This will be equal to what? 1. Okay, this will be my value. Okay, fine. So this will lead to what? Value 5. Oh, sorry, 1. 1. Okay, now try to solve the second problem. If A is my same matrix 3 4 0 2, then if eigenvalues of A inverse is lambda 1 and lambda 2, I want to find lambda 1 multiplied by lambda 2, lambda 1 plus lambda 2. Okay, so this A matrix we have found lambda is what? Lambda is 3 and 2. No? So if we wish to find the eigenvalues of A inverse, this will be what? 1 upon lambda 1, 1 upon lambda 2 from linear algebra theory. So this means this will lead to 1 upon lambda 1 means 1 upon 3, 1 upon, sorry, 1 upon 2. Okay. Suppose dash was here. So dash was here. So here in this question, this was defined as lambda 1, this one defined as lambda 2. So then I need to find lambda 1, lambda 2 plus lambda 1, lambda 2. Okay. This expression I need to find. So this will lead to what? 1 upon 6 plus 1 upon 2 plus 1 upon 3. If you do that, 6 will be the LCM. 1 plus 3 plus 2. This will be equal to 1 only. Okay, so this value will be 1 only. Okay. Okay, good. Good. Now we will solve the other problem. The eigenvectors of a matrix, say matrix 3, 4, 0, 2 are U and V. Then we want to find U dot V means the inner product of U and V divided by the norm of U and V. Okay, this I want to find. Okay, let me add one page here. Okay, so this problem 5 we want to solve. So the A was what? 3 4 0 2. Okay, this was my way. This lead to my lambda equal to was lambda equal to 3, lambda 1 equal to 3, lambda 2 equal to what? Lambda 2 equal to 2. Okay, now for lambda 1, what I can write? A V1 will be equal to lambda 1 V1. Okay, A is what? 3 4 0 2. V1 we wish to find lambda equal to 3, lambda 1 equal to, so V1, oh, I will say, suppose this V1 I write here at, this is my V1, this is my small, okay, V1 V1 V2. Okay, similarly here V1 V2 small. Okay, now you multiply it, then what will get? 3 V1 plus 4 V2 will be equal to 3 V1. From the first equation we will get, and 2 V1 equal to, sorry, 2 V2 will be equal to, this problem we can solve using the system of linear equation solver also. So this and this will be cancelled. So from here we will get V2 will be equal to 0. Once we have got V2 equal to 0, then any value of V1 will lead to a eigenvector. So here for V1 what we will get? The V1 we will get V2 is 0, and any value of A in V1 in place of V1 will lead to a eigenvector. Okay, this is my eigenvector V. Okay, corresponding to lambda 1. This is an eigenvector. So any scalar multiple of this will be an eigenvector. So I can remove this A, which is an arbitrary number. So this I can write as 1, 0. Okay, this is my normalized eigenvector. Okay, similarly for lambda 2, I can find A. A is what? 3, 4, 0, 2. So here small v1, small v2 will be equal to lambda 2 equal to 2. So v1, v2. This will lead to equation 3v1 plus 4v2 equal to 2v1. Okay, and second equation will lead to v2 will be equal to 2v2. Okay, so if you see here, from here what we will get? From here we will get v1 will be equal to minus 4 v2. Okay, and this will always satisfy. So I can write corresponding vector v will be equal to v1. I can write minus 4 v2. Okay, minus 4 v2, and this will be my v2. Okay, so any linear combination of this will be a eigenvector. So I can write v will be equal to minus 4 1. Okay, if I normalize it, so this v will be equal to what? This v will be equal to what? 1 upon root 17. 1 upon root 17 minus 4 1. Okay, so suppose this one I have expressed as first one I have expressed as u, and this is my v. Okay, this is my v, this is my v hat. So what I want to find now? I want to find now u dot v divided by under root of u dot u v dot v. Okay, so u dot v will be what? Corresponding element will be multiplied. So minus 4 will be multiplied to 1, and this 1 will multiply to 0. That will lead to minus 4 divided by u dot. This will be the magnitude. So its magnitude will be 1, and its magnitude will be what? 17 square. Oh, sorry, 17. Minus 4 divided by root 17. This will lead to some value. What will be the value? It will be equal to 0.97. Okay, so this value will be what? Its value will be 0.97. Okay, now if same matrix A inverse eigenvectors are u and v, since we know if eigenvectors for A is u and v, the same eigenvector will be for A inverse. Means what? The same u and v will get for A inverse also. Means the value will be same 9.7. Okay. Okay. Now next problem is for A transpose. For A transpose, eigenvectors are u and v, then we wish to solve or find the same value. Okay. So what will be the value of this expression? You please, like I have solved, you also try to solve. Okay. Then you will get the same value 0.97, but the eigenvectors will not be the same, and eigenvalues also. Maybe I should solve here. So what will the value? A transpose will be what? Earlier 3402, 3402. This will be, then what will be my characteristic determinant of a minus lambda I? This will be my characteristic polynomial characteristic equation that will lead to 3 minus lambda and 402 minus lambda equal to 0. This will lead to lambda equal to 3 and 2, like that earlier. Okay, means transpose and this will have the same eigenvalues, but eigenvectors will come as different. The you will get here will be different, 1 4, and v will come as 0 1. If you solve like that, and if you find the same expression u dot v divided by u dot u v dot v, it will come the same value, 9.7. Okay, I hope you have got the answer. Okay, now eighth question. Suppose, now the eighth question we have, suppose n cross n real symmetric matrix A. Okay, it has an eigenvalue ai plus bi under root 1. Okay, so from linear algebra theory we know for eigenvalues of symmetric matrix is always real. Okay, eigenvalues of a symmetric matrix is always real. Means what? This bi will always 0. So this will be a wrong answer. This will be a wrong answer. This will be my correct answer. Okay. Okay. So this you should know. Eigenvalues of symmetric matrix is always real. If you remember your linear algebra theories, you would have known that this value. Okay. Now the last question for today. For an M cross N real matrix. Okay. B is defined as A transpose. Then it has some distinct eigenvalues. So these eigenvalues are distinct. So we need to find the eigenvectors. Okay. So B is what? A transpose. What is the dimension of this M? M cross N, and dimension of A transpose N cross M. This will lead to some B with dimension M cross M. Okay. So eigenvectors will not have n dimension. This will not have. It will have m dimension only. And its eigenvectors may or may not be orthogonal. We can't say whether it will be orthogonal or not. So this will be my right answer. Okay. Since it is m cross m, means eigenvector will be m dimensions, and maybe or may not be maybe or may not be it is orthogonal. Okay. Fine. Now what we'll try to do? Now we will try to write a computer program, or rather I will show a computer program how can we can use power method and inverse power method to find the eigen values and eigenvectors of a square matrix. Okay. Should we move? Should we move ahead? Have you understood everything? If you have any doubt, please ask. Okay. So suppose we have a matrix. We have a matrix A equal to. We have a matrix A equal to some random matrix I am defining. Some random matrix 1, 3, 5. Okay. 10, 8, 20. Okay. Similarly, minus 20, minus 60, minus 62. Okay. This matrix I have. I want to find all eigen values and eigen vectors of eigenvalues and eigenvectors of this matrix A using power method and inverse power method. Okay, this is my some random matrix. I want to find all eigenvalues and all eigenvectors of this matrix using power method. Okay, so first I will find the dominant, means the sub maximum magnitude wise maximum eigenvalue using the power method. Okay, so what was the algorithm for power method? I simply copy from here. Okay, so this is the formula for power method. Na? So some initial guess v0 we had 0 I will make. Then by using this formula I will find v at different iteration, and by using this formula I will find the eigenvalues at some iteration, and I will put some stopping criteria k plus 1 minus k kth iteration, this mod value less than epsilon. Okay, if it is smaller than some epsilon or maximum allowed error, this is what maximum allowed error. Okay, I will put this condition. Once this condition is satisfied, my iteration will stop. Okay, and whatever the value I will get, that will be my the dominant eigenvalue and its corresponding eigenvector. Okay, so let us see how we can do this. So this is program I have made in MATLAB. So this is nothing but I have put some clear, or if suppose I have some variable already stored in my workspace, but I just want to remove that. Then I have defined the matrix A. Then what? That to find the highest value of largest eigenvalue and eigenvector, I will use power method. Okay. In power method, what I have done, I have called the function power method. This function I have made. This will return me eigenvalue and eigenvector. Okay. Then I will display the maximum eigenvalue as eigenvalue E of value, and I will display corresponding eigenvectors as E vector that I will found from the function power method of A. Okay. So let us see what is my power method function. So this is my function definition. Okay, this is the definition of the function. This will return me some lambda and some v hat new. Okay, and this is my function power method. This will take input as a. Okay, so I have defined I do not want to go more than 100 iteration. Okay, I have defined the maximum allowed error as 0.01. This you can define other. Then I have some initial, some large errors for starting the process. Okay, some lambda new and lambda old I have defined as 00. Initial guess, here I have taken 101, but you can take any random v you can take. Okay, this is my initial guess. Then what will be my hat? Hat will be what? V initial divided by norm of v. Okay, this will be my v hat. And initially I have defined v hat new as v hat old. Okay, then some counter I have taken num equal to 1. Then I have put while error is greater than maximum error. This is my maximum allowed error. Once my error will be either equal to or less than this maximum allowed error, my program will start, or my num will be greater than maximum iteration. Okay, here I have, okay. So my while loop will start like that. First I will assign the last iteration value v hat of new as v hat old. Okay, here I will define. Then v hat new will be equal to a multiplied by v hat old divided by norm of a multiplied by v hat old. This is the formula, na? This is the formula. V hat new will be equal to a multiplied by v hat old divided by norm of a multiplied by v hat old. This is for the formula I have written here. Okay. Okay. This is the main formula. Now what we'll do? We'll find lambda old value. This lambda old value will be what? This lambda old value will be what? This will be dot product of a. This will be dot product of a multiplication of a v hat and dot product of v hat. Okay, so lambda old will be dot product of a multiplied by v hat old and v hat old. Okay, similarly new will be what? A multiplied by v hat dot product of v hat. Okay, this will be lambda new. Now I will find error will be what? Absolute value of lambda new minus lambda old. Once this code will run, that code will return me lambda new and v hat new. This will be saved in my e value and e vector value. Okay. Then this will be printed. Okay. Then what I will do? I will use the inverse power method to find the lowest eigenvalue and other eigenvalues. And corresponding eigen vectors. Okay. For that, what I will do? I will define some shift. This shift will do nothing but the q that we have defined earlier. Na? So I will simply copy the formula from there. Maybe I think I have written in my down side also. Okay. So this is the formula I have. Na? This a minus qi will be equal to a minus qi multiplied by v hat, or rather v. This is the formula. A minus qi v at k plus 1th iteration will be equal to v at kth iteration. This is my system of linear equation. From here I will find v at k plus 1th iteration. Then how will I will find the lambda? The lambda I can find by using this formula. Na? A minus qi v will be equal to lambda minus q v. This is my shift in the function. Okay, shift. Okay, so from here I can write simply what? If lambda minus q will be equal to what? A minus q I v hat dot product of v hat. Okay, From here I will get lambda as q plus this whole term. Okay, so these two are my main equation. So how I have implemented that now, see. And this q will define what value I want to find. If q is 0, I will find the minimum value. If q is some value, some other value, then I need to check lambda. Suppose jth I want to find, so lambda at jth, if lambda I minus q, I goes for other than j, other than j, then the corresponding eigenvalue I will find by using q value. Then I need to choose q carefully so that this inequality is satisfied. Once this inequality is satisfied, then the corresponding eigenvalue and eigenvector I will get by using the function. Okay, which function? This inverse power method. So how I have made this function? This function take input as two things. First is the matrix that we wish to find the eigenvalues and eigenvectors, and the shift q. Okay, then I have find the size of this A matrix, m cross m, whatever the size. Maximum iteration I have defined 10, and some maximum error I have defined. Okay, some initial error I have defined. Now I have taken v as some random value. Now earlier what I have taken, v equal to 1 0 1. Now I have said that the v can take v as a random value also. So here I have taken v as some random value. Okay, then I have normalized it and defined v hat new equal to v old and initial lambda new equal to 0. Okay, now what I have done, while my error similar to that, while my error is greater than maximum allowed error, or my number of iteration is greater than maximum allowed iteration, my while loop will run. First, what I will do, I will lambda old, I will define lambda old will be equal to lambda new. Means what I want to do, I am doing lambda k plus 1. Sorry. I am trying to define lambda kth here. Lambda kth will be equal to lambda k minus 1. Okay, this is what I am trying to do. Oh, sorry. This is what I am trying to do in this line. Okay, so in some lambda old I want to store the previous value. Okay, then what I will do, similarly I have defined here v hat of old equal to v hat of new, means the previous value will be stored in the old. Okay, now this and these two equations we have now, this equation and this equation we will use to find the value at this iteration. So v hat new will be equal to a minus shift multiplied by, this is eye, this is nothing but the identity matrix in MATLAB. Okay, so what I have done, I have simply done here a minus qi divided by v hat. Okay, so simply I have solved this vk plus 1th vkth. Okay, so simply I have solved here system of linear equation. So what I have done here, I have solved the system of linear equation here. System of linear equation has solved. I can solve by defining some function. See here, I have commented one thing. This is the commented part. If you see, so this is the inbuilt function in MATLAB. Okay, if what I do, if I do math in MATLAB, x equal to a backward slash b, I will solve ax equal to b type of linear equations. Okay, system of linear equation. Okay, so I have used simply the inbuilt MATLAB function. What you can do, you have already made the Gauss elimination function. Use that Gauss elimination function to find the new you had to solve this system of linear equation. Okay, once I have solved, I have simply just normalized it. Here what I have did, I normalized it. Okay, once I have normalized it, I want to find lambda new. That lambda new will be to shift plus dot product of, see here, q plus dot product of v hat and a minus qi multiplied by v hat. This term I want to express here. So shift plus dot product of v hat of new, and here it will be what? A minus shift identity matrix multiplied by v hat of new. Okay. From here I will find lambda new. Then I will find the error lambda new minus lambda old. Then num equal to num plus 1. Okay. So from here, whatever the input in the main function, this is my main function. Whatever the input I will give here, from this input, it will determine determine which condition it satisfied from this inequality, and then corresponding from this inequality, whichever is will be satisfied, it will find that eigenvalue and eigenvector. Okay. Okay. Clear? Clear? Please respond. Please respond so that I can show you the code now. Okay. Okay. So now I will stop share from here. Now give me 1 minute. I will connect from my laptop and then show you whatever I have done. Just give me 1 minute. I'm joining from my laptop. Okay. I hope you are able to see my screen now. Okay. So this is my A, whatever I have defined here. Okay. And this is the inbuilt function in MATLAB. Okay. This is my inbuilt function in MATLAB to find the eigenvalue and eigenvector. This what I am doing. I will just after doing it, I will just check whether I am finding the correct eigenvalues and eigenvectors or not. Okay. So suppose I have defined shift as 0. Okay. Here I have I am calling the power method function to find the highest eigenvalue, and here I am calling the inverse power method function to find the minimum eigenvalue. Okay. Okay. So simply if I run this, see, this is my highest eigenvalue that I have found. This is my highest eigenvalue that I have found, and this is corresponding eigenvector. This is my minimum eigenvalue, and this is my corresponding eigenvector. Okay. Okay. Now if I uncomment this part, the inbuilt function, and I run this. Okay. Okay. Now I run whole code. Okay. So the same eigenvalues and eigenvector that I have shown. Now if I see E vector E value. Okay. E vector E value. So this is my E vector. This is my E value. These two, what I have done, this from the inbuilt function. Okay. And this eigenvalue and this eigenvectors we have found from our code. Okay. So if I go here Now I will cut simply this. Okay. Now you see the eigenvalues. Okay. Eigenvalues. Okay. This is my minimum eigenvalue. This is my maximum eigenvalue. Okay. This is minimum eigenvalue. This is maximum eigenvalue. And corresponding eigenvectors. This first column is corresponding to the minimum eigenvalue, and this second column is corresponding to uh, this first column is corresponding to the minimum. This second column is corresponding to the maximum eigenvector corresponding to the maximum eigenvalue. Okay. Now you see here, you see this vector and you see this vector. This vector and this vector are same, only minus is multiplied. If A is an eigenvector, then its scalar multiple will be the eigenvector. So this you see, this you see, we are getting the same. This you see, and this value you see, we are getting the same. Similarly, minimum here, and corresponding this eigenvector, and this is the corresponding eigenvector. Okay. Now I want to find the other eigenvector. So here, what is the eigenvalue? 22 minus 22. So I need to get the 22 value, no? So for that I need to change the shift value. Okay, so I have changed it to -5, suppose. Okay, -5. Now if I run it, see, I am getting still the same eigenvalues and eigenvector. Why? Since minus 1.25 and -5 is my shift. It is much closer to minus 1.25, whatever is the value, my here see, my shift value -5 is closer to this value compared to this value. That's why it is giving me this eigenvalue. Okay. If I increase it to 10, now if I run it, still I am getting the same answer. Why? Since -10 is closer to -1.2785 compared to -22. If I simply put here 13, suppose 13, okay. Now I run. See, now it is given 22 and its corresponding eigenvector. Okay, 22 and its corresponding eigenvector. Okay, clear? Okay, now you can see the power method. So the power method that I have explained, here it is written. Similarly, inverse power method that I have explained, it is written here. Now if you see in inverse power method, what I am doing in this line, I am using this inbuilt function to solve the linear equations. Okay, now I will use the function that has been built by user to solve the system of linear equation. Control C, Control V. To solve the system of linear equation, I will use this Gauss ELI. This is the Gauss elimination function that I have made. Now I will show you the function. Okay. So this is a function forward elimination using scaling and partial pivoting in Gauss elimination. Then forward elimination ends and backward substitution starts. Okay. So this, I think I have shown in the last week problem solving session how to make the Gauss elimination code. This function I am using here now. If I run, see, same 22 I am getting earlier, whatever I was getting. Means what? Now rather than using the inbuilt function, I have used the function that has been made by the user, Gauss ELI function. Okay. Now if I change this 13 to 0, I will get the minimum eigenvalue, means minus 1.25, so minus 1.785 and corresponding eigenvector. Now you tell me any other matrix that I want to solve. Simply I will put the value here and I will find the eigenvalues and eigenvectors. but I need to make sure that the whatever the shift value I am giving, whether that is satisfying the criteria or not. Lambda j minus q absolute must be less than other lambda I minus q absolute value. Okay, this I need to make sure. Now please respond whether you are able to follow or not. Okay, so what else you want me to do now? Since I am not in the campus now, I'm at my home. That's why I have not written in the Python format in the live class. There is some issue of internet connectivity here. But if you know the procedure, if you know the algorithm, if you know the pseudo code, if you are able to write the pseudo code, there is no issues. Okay, you can write the program in any language. Okay, so have you understood whatever we have covered in this lecture, in this problem solving session? What we have discussed first? So what we have did first? First we have seen the LU decomposition method. In LU decomposition, we have this coefficient matrix. We have decomposed into a lower triangular and upper triangular matrix. Then we have found the some intermediate T by using LD equal to B system of equation without doing any elimination, simply doing the forward substitution. Then we have solved Ux equal to D by using backward substitution. We find the value of X. This is very useful when we wish to solve Ax equal to B1, B2, B3 kind of set of system of linear equations. Okay. Then we have seen the similarity between the Gauss elimination and LU decomposition. Although this is not very suitable method, since if we have used the Gauss elimination method, then there is no need to go for LU decomposition. We can, if we have used the Gauss elimination, then we have solved the problem. So there is no use to use. There is no need to use this LU decomposition. But for the sake of completion, we have seen that the similarities between the LU decomposition and Gauss elimination. Okay. Then we have seen the Doolittle and Kraut method for LU decomposition. Okay. Then we have seen how to solve system of nonlinear equation. This system of nonlinear equations is converted into system of linear equation. Linear equation. How? By using Newton-Raphson method. Okay. Then we have solved it. We can solve it using Gauss elimination or other linear solvers. Okay. There we have learned about a matrix that is known as Jacobian matrix. Jacobian matrix is defined as J I will be equal to del of f of I divided by del of xj. Okay. Then we have seen the iterative linear solvers, which is what? Jacobi iteration method and Gauss Seidel method. In Jacobi iteration, we have seen the generalized format. Then in Gauss Seidel method, which is similar to the Jacobi method, only one change was that the latest value of ui is used, okay, in RHS. Then we have seen the successive over relaxation method in Gauss Seidel and how it can slow the convergence or fast the convergence and what is its use. It may be used to stabilize the solver, or it may be used to fast the solver. Okay. Then we have seen the convergence criteria, which is known as Scarbo criteria, which is although developed for the Jacobi iteration, but it can be used easily, can be applied for, it can be applied for Gauss Seidel methods also. Okay. What it was? It was that the coefficient matrix should be diagonally dominant. Diagonally dominance means what? Modulus of AII should be greater than or equal to the summation of other elements in all the rows, and in at least one row it should be greater than. Okay. Then we have seen how we can find the eigenvalues and eigenvectors of a matrix, of a square matrix using numerical method. Okay. Then first we have revised the method, analytical method that is used to find the eigenvalues and eigenvectors of a square matrix. There first the characteristic equations written, then roots of the characteristic equation was the eigenvalue, then eigenvectors has been found. Okay. Then we have discussed about power iteration method, which is a numerical method to find the dominant eigenvalue of a square matrix. Okay. And its corresponding eigenvector. Then we have seen the inverse power method and shifting of inverse power method to find the other eigenvalues and corresponding eigenvectors. Okay. This was very important criteria to find any eigenvalue and corresponding eigenvector. Then we have solved some sample problems that are similar to the assignment problem that will be given to you in week 4 assignment. Okay. That was very easy. We have seen all the problems we have solved here. Then what we have did? Then we have taken some arbitrary matrix and we have found all eigenvectors and eigenvalue of the matrix using a power method and inverse power method by making a computer program. Okay. So main equation, whatever the main equation first we have written, these four are main equation we have written. Then we have made the functions for power method and what inverse power method. Okay. So should I stop now? If you want me to add anything in this discussion hour or in this power problem solving session, please tell me. Okay. So just to, if anyone seeing this video, I am Kesha Yadav. I am a PMRF fellow at IIT Kanpur. So I am taking this problem solving session of this NPTEL course ME111. Okay. Applied numerical method. Okay. So I think I will stop now. Should I end the meeting now?